Hi everybody. Today we will lecture you about the interface system that we talk about the solid, liquid, and gas phase. Mostly we talk about gas phase is important because the solid liquid property is quite constant with the change of pressure or temperature. First of all, you introduce you the result that you can find is some chemical physical property like density, vapor pressure, solubility are following like for example like early chemical engineering handbook. It is a famous handbook. I think I load in the Google Card tomorrow for you. Do this, or you can have a look at the CRC handbook for chemistry and engineering or TRC database in chemistry and engineering. Like and also like the physical and thermodynamic property of pure chemical. Like, also you can look at the World Wide Web of your data that's from novel online database. But the HUT allow you to download or use online in the novel, novel online database. And also can use your handbook online database. It is the area or the resource that you can find the substance property like physical property or chemical property. That's something we will talk to you in this lecture. For the first system, I will talk about the liquid solid density of a mixture. For the pure system, I talk to you in the earlier of this class, but in this, I will talk only the mixture, how to determine, how to calculate the mixture, like density of mixture of liquid density, solid density in the mixture form. We have at least two formula. I will introduce you. But the first formula, we can calculate the density of mixture by we call this low bar. Low bar is the average density. Right? 1 divided by average density equal to summation of xi divided by low I. Xi is the mass fraction of component I. Right? Low I is the density of component. For example, in the liquid system, we have toluene and xylene. Xi mean mass fraction of toluene divided by density of toluene plus mass fraction of xylene divided by density of xylene. You get the 1 over average density. You can use this, or you can use the second formula. Right? Average density equal to summation of xi low I. Xi is mass fraction of component I. Low I is density of component. But mostly the first equation, equation 1 is the base for mixture with similar molecular structure, either straight chain hydrocarbon or straight chain hydrocarbon, something like this. And also this figure, right, show you the experimental data and the formula estimated using these two equations. Right? The solid symbol, right? The solid symbol means the experimental value, experimental value. And this is the cube symbol is estimated from equation 1. From equation 1 side. This is when percent weight of non-aqueous component, this mostly percent weight of the solute increase, density increase. Like for sulfuric acid and water system. You can see that for sulfuric and water system, equation 1 or formula 1 is better for equation 2. That's right, because formula 1, the data is close to the real data. Real data means the experimental value. It's better when you evaluate or estimate by formula 1. But formula 2 is there are some deviations. Right? There's some error. Yes. But for the system of methanol, right, CH3OS and water, you can see that both formula, right, formula 1 and formula 2 is best estimator, right, because it's close to the experimental value. Experimental value. Yeah. But you can use both this of equation, both of this equation, but the first equation is based for a mixture with similar molecular structure or something like this. Right. But you can use for this, the first one is better. Okay. I will introduce you about the solid property only the density mixture, and the next we will talk about the gas. First, I will introduce you only the ideal gas, perfect gas. Mostly the gas will be ideal or perfect gas is mostly as low pressure. As high pressure, the gas will follow the real gas, but I didn't talk to you in this class. Okay, you can study in the thermodynamic subject, like for the real gas. Right. A gas at certain temperature and pressure might behave ideally, and at a different temperature and pressure not behave ideally. A gas behavior is ideal. That means it's followed this equation. If the gas behavior follow this equation, we call this gas is ideal gas. Like PV equal to nRT or PV dot equal to N dot RT. V is volume. N is number of mole. That's right. V dot is volumetric flow rate. That's right. N dot is molar flow rate. Something like this. You can use this. R is a gas constant. Right? It is depend on pressure, volume, number of mole, temperature, and T is absolute temperature will be Kelvin or Franklin. Right? And also this equation may be expressed in terms of PV hat equal to RT. V hat means V divided by N. We call it is specific molar volume. V dot is the volumetric flow rate. V hat is specific volume. This divide volume by mole. Okay. 1 mole of an ideal gas at 0 degrees Celsius and 1 atm is occupied 22.415 liter. We call it the standard state condition. The standard state condition means gas at 0 degrees Celsius, 1 atm, and 22.415 liter. This is mean the standard volume. Okay. The gas constant has a unit of pressure multiplied volume divided by mole multiplied temperature. So, or it means energy divided by mole multiplied by temperature. This is the unit of ideal gas constant. Okay, ideal gas equation also work well under some conditions at above 0 degrees Celsius and pressure below 1 atm. And the error between the ideal and true, we can calculate that the error from the ideal gas is ideal gas minus 2 divided by 2 multiplied by 100. Right. Or you can calculate the absolute value should be less than 1%. Okay. If you calculate the percent error, if it's less than 1%, okay, we can assume this gas is follow the ideal gas. That means if V ideal, V hat ideal or specific volume equal to RT divided by P greater than 5 liters per mole, aside for diatomic gas, or RT over P greater than 20 liters per mole for auto gas, okay, we can assume this is the ideal gas because the error is less than 1%. Right? For the case, the gas is the error. Right? X ideal minus x2 divided by x2 multiplied by 100%, or V ideal greater than 5 liters per mole for diatomic. Diatomic means 2 right? Or greater than 20 liters per mole for the other gas. Okay, we can assume the gas is ideal. The specific volume is V hat liters per mole is equal to m bar divided by m is the molecular weight. That's right. Rho is density. And then you can calculate density is Pm by R. M bar is average molecular weight. From the ideal gas, PV equal to nRT or PV dot equal to N dot RT. Maybe P equal to RT. And then you can calculate mole, you can calculate density. The density of gas equal to Pm divided by RT. And use the ideal gas. Calculate the power. Previously, I talked to do the standard condition. You can calculate the property of gas and related or referent to the standard condition. For this case, we flow rate as standard condition, S is standard condition, pressure as standard condition multiplied by specific volume as standard condition equal to RT as temperature as standard condition. Right? Standard condition. Okay, if you compare between standard condition and actual condition, right? Actual condition, okay, have PV, sorry, have PV equal to RT, right? PV equal to RT. PV at actual condition divided by PS, VS, PV equal to nRT. R is constant, that's right. R is constant. Okay, you can cancel R, And this is the P-act because P-act is divided by N already. Okay. nRT divided by RTS, right? nRT divided by RTS, cancel, you get PV over PS, React, equal to NT divided by TA. And then if you use the standard condition, you can calculate the property, pressure, volume, number of mole, or temperature for the actual condition. Yes, and this table shows you the standard condition of the gas. We have show you at 3 systems, right? SI unit, CGS unit, American Engineering unit. Right, the standard condition is SI mode at 0 degrees Celsius or 273.7 Kelvin, 1 atm. And VS is 0.0222415 cubic meter. Standard number of mole is 1 mole. This is the standard condition. Like for CGS unit, also the same. Temperature is 0 degrees Celsius or 273 Kelvin. PS is 1 atm. Right. VS is 22.415 liter. And S mole, okay, 1 mole. And if you use the American Engineering unit, you get temperature standard is Rankine, it's 492 Rankine. Pressure is 1 atm also, and VS is 359.05 cubic feet. Mole is 1 pound mole. 1 pound mole. And okay, we can conclude that the standard specific volume equal to 22.4 cubic meters per kilomole. That's right, cubic meter per mole or kilomole. Let's say. As at STP, standard temperature pressure. STP means standard temperature pressure, or equal to 22.4 liters per mole. That's right, they say cubic meters per mole. Because it cubic meters 1,000 liters equal to 1 cubic meter. 1 kilomole equal to 1,000 mole. That's right, they say. It's the conversion unit. Okay, 22.4 liters at STP divided by mole, or equal to 389.05 cubic feet per pound mole at STP. Right. Sometimes we call the term SCM is standard cubic meter, denoted as cubic meter STP, or standard cubic feet is SCF, denoted as cubic feet at STP. Right. For example, if the volumetric flow rate equal to 18.2 SCMS, represent SCMS. SCMS is standard cubic meters per hour at 0 degrees Celsius and 1 atm. Please note that the standard temperature and pressure is 1 atm and 0 degrees Celsius. That's right. Celsius and 1 mole. For example, we show you how to convert from standard condition. We consider the butane at 360 degrees Celsius. 3 atm, absolute. Throw into a reactor at a rate of 1,100 kg per hour. We calculate the volumetric flow rate of the stream using conversion from standard condition. Okay, standard condition, if you remember that, you can use this formula. Or you can use this relationship. PV divided PV SVS equal to NT divided TS. The first step, you have to calculate the molecular flow rate. You know flow rate, mass rate, and then you change mass rate aside to the molecular flow rate. For this case, you can calculate by divided by mass rate by molecular weight of butane. The molecular weight of butane is equal to 58.1 kilogram per kilomole. And then you can calculate molecular flow rate or N dot at 19 kilomole per hour. And temperature, the temperature is 360 degrees Celsius. You have to convert to Kelvin. That's right. 360 plus 273. You get 633 Kelvin. And the pressure is atm. And then you use the formula like PV dot divided by PS VS equal to N dot T divided by TS. And then you can solve for V dot, that's right, volumetric flow rate, equal to N dot VS T over TS, PS over PS, N equal to 19 kilomole per hour. Okay. VS standard volumetric specific volume is 22.4 cubic meters ATP per kilomole. Actual temperature is 633 and standard temperature is 0 degrees Celsius or 273. Standard pressure is 1 atm. Actual pressure is 3 atm. And then you can calculate volumetric flow rate is 329 cubic meter per hour. You can use the relationship between actual condition and standard condition for this example. For the next example, right, we study the effect of temperature and pressure on volumetric flow rate. 10 cubic feet of air at 70 Fahrenheit and 1 atm, right, is heat to 610 Fahrenheit and compressed to 2.5 atm. Okay. For this case, what volumes does the gas occupy in its final state? What is the volume of this gas at the final state? Okay, the first step is easy. You have to draw the flow chart. Okay, for this process, right? We don't know the mole of the air. Okay, we assume N is the mole of air in terms of power mole. We use power mole because it is taught in the American engineering unit. And the final state also N mole, also the same, mole air. Okay. In the initial step, we know like V1 initial step is 10 cubic feet, that's right. T1 is 70 Fahrenheit. You can convert from Fahrenheit to Rankine because the absolute temperature for Fahrenheit is Rankine. That's right. And the initial state of pressure is 1 atm. In the final state, after compress, that's right, or the heat either compress, V2 we have to calculate. Right. V2 is 610 Fahrenheit, and then you convert to 1070 Rankine. And P2 is 2.5 atm. 0.5 atm. Okay, for this case, you can use the conversion bed. You can compare from the first state to the second state or initial state with the final state. It is the same technique when you compare with the standard. We have two states, right? The standard actual. If you know standard, you can calculate actual. It's also, we know the first step, the second step, initial step, and final step. You can compare this. For example, right, from the ideal gas, if we assume this is follow the ideal gas, is quite low pressure. Okay, the final state, we call it state 2. P2 V2 is equal nRT2. Right? The first state or initial state is P1 V1 equal to nRT1. With this not N1 or N2 because N1 and N2 is equal. So number of mole is the same for initial state and final state. But there is no reaction, there is no nuclear reaction. Okay. The mole is the same. Right? And the gas content is the same. But the gas content is, and then you divide this P1 V1 by P1 or P2 V2 by P1 V1. Okay, P2 V2 divided by P1 V1 equal to nRT2 divided by nRT1. nR is cancelled because it's the same from the initial state and the final state. Okay, for this formula, you can solve for V2. because we know T2, we know T1, we know V1, we know P1, we know P2. You can solve for V2. That's the case. V2 equal to P V1 multiply P1 over P2, T2 over T3, P1. Okay, V1 is 10 cubic foot, right? P1 is 1 ATM. P2 is 2.5 ATM. P1, P2 is 1070, and P1 is 500. So that you get is 0.08 cubic feet. Cubic feet. You can compare, right? The first state is 10. The second state is 8. Right? The volume is decreased. This is correct because the first state, and then you compress because gas or ideal gas, the volume will reduce with the state that you or reduce based on the something like the compress it, you decrease the pressure or you increase the pressure, you compress, the volume will decrease. For the next example, right, we talk about the standard and true volumetric flow rate. The flow rate of the methane steam at 285 Fahrenheit and 1.3 atm. As I with measure with the orific meter. Orific meter is the equipment used to measure the flow rate. You use this to measure the flow rate of the methane steam in the gas phase. The calibration chart for the meter indicates that the flow rate after you measure by orific meter, you get the flow rate of methane is 3.95 multiplied by 10 power 5. SCMFS, it means standard cubic feet per hour. Okay. The question is calculate the molar flow rate and the true volumetric flow rate of the steam. Okay, recall that SCFM means standard cubic feet per hour. For this case, you calculate volumetric flow rate, right? Equal to, what is this? This is the volumetric flow rate. That's right. V n equal to V multiplied by the standard state. You can compare with the standard state. This is the volumetric flow rate of this case. 3.95 multiplied by 10 power 5 cubic feet per hour. But you know, at the standard state, for 1 mole, 1 pound mole at the standard state, we know the standard volume. You only compare. Yes, yes. For the standard state, for 1 pound mole is equal to 358 or 59.05. Okay. You divide this by this is the action state. It's the standard cubic foot. But you know, that's right. Or this equal to 1 pound, and then you can calculate the mole flow rate. Okay. And then you can calculate the molar flow rate or true volumetric flow rate of the steam. The true volumetric flow rate of the methane is calculated using the previous technique by compare between the first state and the second state. That's right, the first state and the second state. For this case, the first state is the P1 equal to 492 Rankine, P1 equal to 1 atm, V1 equal to this. The first state, this is the first state. And the second state, the first state is from the measured, and the first state is T2 is this, for this case, right? P2 for this case, and V2 we don't know, right? V2 we don't know. Okay. For this case, you can calculate like, you can use this, the same, that's right. P2 V2 equal to NR P2, P1 V1 equal to NR P1 because NR is the same, NR is the same, you get P2 V2 divided by P1 V1 equal to T2 V1 V1. You get this. And then you substitute V1, T2, T1, P1, P2, you can calculate the true volumetric flow rate like this. Previously, we talked about the gas only the one state, one single phase. But for the next slide, we talk about the ideal gas mixture. Ideal gas mixture. For this case, we will talk about the partial pressure. Because PA is the pressure that is exerted by mole of atom A with the same total volume pressure P. And VA is the volume that would be occupied by Na mole of A alone at the total pressure P and temperature T of the mix. Okay. For this case, if you calculate the partial pressure of gas A in mixture, we call PA. PA means partial pressure of A. P means total pressure. Okay. Partial pressure A multiplied by total volume equal to mole A multiplied by total temperature, or temperature is not total. And then you can calculate the mole fraction from the mixture. The mole fraction of gas A you can calculate by the partial pressure divided by total pressure. Okay, for this case, partial pressure of A divided by total pressure is equal to Na divided by total mole. You get mole fraction of. For this case, you can relate it like partial pressure equal to mole fraction of A multiplied by total pressure. Okay, this is the formula for partial pressure that related to mole fraction. And then moreover, for the gas mixture, the total fraction is 1. If we have like Ya plus Yb plus blah 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 equal to 1. Right? This means the same. Pa plus Pb is also equal to Ya plus Yb plus blah blah, and then all of this multiplied by P, you get total pressure. Right? Total pressure is the summation of partial pressure. Right? Summation of partial pressure. That is equal to summation of fraction of each component multiplied by total pressure. We call this is the Dalton law. Dalton law, with the partial pressure of the component of ideal gas mixture adds up to the total. For this case, the total pressure is the summation of partial pressure for each component, or the summation of total pressure multiplied by fraction of each component. Get total pressure. This is the Dalton law. This is used for the ideal. Moreover, you can calculate the Amagat's law. That's like PVA equal to NART, and then you divide it by PV equal to nRT. VA divided by V equal to NA divided by N. You get one fraction. VA equal to YAV. That means VA plus VB equal to V. Because this is the Amagat's law. VA divided by V is the volume fraction of A in the mixture. For this case, we can also for ideal gas, mole fraction equal to volume fraction, or mole percent equal to volume percent for the ideal gas. This is the Amagat law. Investigate this. Right? VA divided by V equal to NA divided by N equal to YA. This means mole fraction or mole percent equal to volume percent, or volume fraction. Okay. For example, right, we have ideal gas mixture contain 30% methane and 70% ethane by volume. By volume mean 30% V divided by V of ethane and 70% V divided by V of ethane. It's equivalent to 30% mole of methane equal to 70% mole of ethane for this case. Okay. It shows you the example of the material balance on evaporator and compressor. We have two components. Evaporator means the evaporate of liquid to the vapor, means change phase of liquid phase to the vapor phase. Compressor, we compress this electrolyte, increase the pressure. Right? We increase the pressure. The volume of gas is reduced. For this case, we have liquid acetone. It's fed as a less of 400 liters per minute into a heat chamber. It is a heat chamber means evaporator, where it evaporates into nitrogen steam. The gas leaving the heater is diluted with another nitrogen. Right? For this case, we mix the liquid acetone with nitrogen. After evaporate, the product gas will dilute with nitrogen steam forming at a mixture rate of 419 cubic meters per minute. That's right, cubic meters per minute. Right. After that, the combined this gas are then compressed to a total pressure of 6.3 atm gate at a temperature of 325 degrees Celsius. Okay. For this case, the partial pressure of acetone in this stream is 501 millimeter mercury. Atmospheric pressure for this system is 763 millimeter mercury. Okay, the question, what is the molar composition of the steam during the compression? What is the composition of nitrogen acetone of the product of the compressor? The first. For the second, what is the volumetric flow rate of the nitrogen entering the evaporator? Is it the nitrogen feed to evaporator? What is the volumetric flow rate? If the temperature and pressure is the same, 27 and 475 millimeter mercury. Okay. After you read the problem statement, you have to draw the flow chart and you get the basis. For this, mostly the basis should be the volumetric flow rate of the acetone or nitrogen for this case. Okay, and then you assume all this as ideal gas, and then you we have to process like evaporator or heater and compressor. Input evaporator we have two steam, right? The first steam is liquid acetone. Okay, you know the liquid acetone in 400 liters per minute, and then you denote N.2 is the molecular flow rate of liquid acetone. Okay, another feed stream is nitrogen. Okay, the nitrogen we assume V1 is volumetric flow rate of acetone, and N1 is the molecular flow rate of nitrogen. And then you specify the system is the nitrogen feed at 27 and 475 millimeter mercury. Okay. The next feed stream is feed to the product out of the evaporator is nitrogen feed at the flow rate of 419. Okay? And N3 means molecular flow rate of nitrogen. Okay? And also the output of the compressor, we denote N4 is the molecular flow rate of the system of the gas mixture. And Y4 is the fraction of acetone. And then you can calculate fraction of nitrogen is 1 minus Y4. That's right. And also the output, the system like 6.3 atm gate. Temperature is 325. And partial pressure of acetone, also for this steam. The first step, you have to calculate molar composition of steam during the compressor. That's right. You calculate N4. And then volumetric flow rate of nitrogen. That's right. Further, you calculate V1. For the first step from the flow chart, in this case, you N2 and N3, this is not unknown. We have V1, N1, N2, N3, N4, Y4, 1, 2, 3, 4, 5, 6, 6 unknown. But for this case, N2 you can calculate from the volumetric flow rate. This is not unknown. N3 you can calculate from the volumetric flow rate. Okay, this is not unknown. N1 you can calculate from the gas property. That's right. This property, temperature, pressure. Okay, you can calculate this V1 N1. You can calculate that. Right? And then we have only N4, Y4, only two unknown. You can solve by math. Right? Because V1, N1 you can calculate based on the condition of the gas. N2 you can convert from cubic meters, right? Volumetric flow rate. N3 you can convert from the volumetric flow rate. Okay. The first step, you have to use this information to calculate N1, N2, N3, V1. First step, you calculate N2, And then you calculate Y4 also. First step, you calculate molar flow rate of acetone. Of the molar flow rate of acetone. For this case, you know acetone is 400 liters per minute, right? 400 liters per minute. And then you have to calculate the density of liquid acetone. The density of liquid acetone is from the appendix table B1. You have to open this table. It's equal to 0.791 gram per cubic centimeter or 791 gram per liter. Okay, you use this. And then you also calculate like the molecular weight of acetone. Okay. Cancel. You get molar flow rate. This is N2. This is N2. You can calculate N2 from the volumetric flow rate. And also you can calculate the mole fraction from partial pressure. This means Y4. Okay, you can calculate Y4 also because you know PA. PA divided by P equal to Y4 mole acetone per mole total. But PA, you know, in pressure gauge, the absolute pressure is equal to pressure gauge as atmospheric pressure. For this case, the pressure gauge of acetone is less than 1 millimeter mercury. Yes, and also the total pressure is 6.3 atm. In the first step, you calculate total pressure. You know PA already. You know total pressure is 6.3, but you have to convert to the mercury, that's 9 millimeter mercury. P equal to P gauge plus P atm. P gauge equal to 6.3 atm. You know 1 atm equal to 760 millimeter mercury, and then you plug atmospheric pressure. For this case, atmospheric is 763. Okay, you get 5,550 mercury absolute pressure. And also, you can calculate Y4. Y4 equal to PA divided by P total. PA equal to 501 millimeters mercury. This is the partial pressure of acetone. In this stream is 501 mercury. This is not to talk is pressure gauge or not. Okay, you assume it is the pressure already. Then you can solve for Y4 and then you can calculate Y1 minus Y4. For this case, you know, right, the composition of acetone and nitrogen in the complex. And then N3, you can calculate N3 also. N3 you can calculate based on information like this. 419 cubic meters standard. In this case, N3, you know the standard cubic meters per minute. 419. But the standard state, you know, is 0.0224 cubic meter per 1 mole. You compare to the standard. And the N4 is 18,000 mole per minute. Okay, you know N2, you know N3, you know Y4. You have only 2 balance, that's right, N1 and N4 is unknown. And V1 you can calculate based on N1. First step, you balance for the overall balance of acetone. Overall balance means you balance overall this. Okay. The overall balance of acetone. Acetone, we have acetone feed is N2. Acetone out of the system is N4 multiplied by N4 multiplied by Y4. Okay. We have no reaction, no generation, no consumption. For this case, we assume steady state process. Flow in and flow out is equal. For this case, input acetone is N2. Output acetone is N4 multiplied Y4. You know N2, you know Y4. You can calculate N4. And then you balance on overall mole balance. overall mole balance, or you balance on nitrogen also is up to. For this case, we overall mole balance. Hormone balance, we have three input, that's right? N1 plus N2 plus NT equal to N4. N1 plus N2 plus NT plus N4 is overall balance. The overall is no generation, no consumption, and no accumulation for the steady state. In this case, you know N2, N3, N4 already. You can go for N1. N1 is 36,200 mole per minute. For the ideal gas, you can calculate V1. T1 and P1, from the flow chart. 27 and less than 75. T1, P1, and then you compare to the standard state. Like previous example, like in this case, V.1 equal to N.1 Vs standard state. That's by Ns. In this case, N is not equal. It's not equal. Like P1, V1 equal to N.1, that's right. P1. And also the standard state Ps, V.S equal to N.S Ts, right? Okay, you divided PV1 by PSVS, P by SVS, and equal to N1 divided by NS, R divided by RR cancel, T1 divided PS, and then you solve for V1, get like this. V.1 equal to N.1 plus VS divided by NS, P1 divided by TS, PS divided by P1. Okay. You substitute all of it, you can calculate V1. N.1 you solve already, right? Standard volume, standard mole, that's right. P1 and standard temperature, standard pressure, and P1. And then you solve for V1, you get this. Okay, we show you the single phase. That's mostly we talk about the ideal gas, how to apply the ideal gas to solve the material balance. For the example, how to calculate the mixture property. I can show you what is the result. You can search for the property like physical property and chemical property. Only in this slide we will talk only the ideal gas. We apply the material balance with the ideal gas system. Okay. The next lecture I will talk to you about the gas liquid mixture. The first is only one component, that's only gas. Next, we will talk about the multiple system, that's multi-phase system. See you for the next lecture.